Hello and welcome to SPH3U Vectors. Before you begin today, please make sure that you have your Vectors notes template ready to jot down various information points as you go. We'll be collecting these tomorrow at class. Okay, so our learning goals. Today we're going to talk about how to distinguish between scalar and vectors, provide some examples of vector quantities relating to one-dimensional motion. When we're finished, we should have the tools we need to solve some problems related to distance, position, displacement, velocity, using vector diagrams. And we should also understand the conventions for representing vectors in algebra. Alright, so quick question. A vector quantity has both magnitude and what? Well, the answer is it has a direction. So it is some value applied through a direction. And the convention for this is pretty simple. We give a magnitude with units, and then in square brackets we talk about the direction that it's applied. Some examples of vectors. The things that we've already covered in a scalar fashion, displacement and velocity, but there are others, of course. You can probably think of some of those yourself. Acceleration, force, lots of other quantities have a direction applied to them. Now, when I come to talk about vector quantities this way, it's interesting to make the distinction between what we've done and what we've achieved. And it reminds me, a buddy of mine talks about working in sales in Microsoft and his boss telling me, I'm not interested in how hard you worked. I'm not interested in what you did. Talk to me about what you've accomplished. Talk to me about results. And these quantities have a lot in common with that. So if we want to talk about displacement, it's not simply the distance we travel plus a direction. It's simpler than that in many ways. Okay, so here's a classic example. The commuter followed the yellow path going home from Manhattan, moved along the river for 8.2 kilometers till he got to the bridge, took the bridge across 1.8 kilometers, and then drove back along the river to get to his home, 4.5 kilometers. When he's finished, he's driven 14.5 kilometers, but his displacement is just 2.7 kilometers north. So there's lots of distance traveled, but really a pretty short displacement. The result was relatively small. And this is the important distinction. So if we take a one-dimensional case rather than a two-dimensional case, we can take Selma walking 2 meters east and then 1 meter west. And we can talk about her distance traveled. We can think of that as the effort versus her displacement, the result. And if we put it in those terms, it should be pretty simple for you to work out. Her distance traveled, she went 2 meters east and 1 meter west. 2 plus 1 equals 3. Very simple. The displacement requires a little more interpretation than that. And so let's do this in terms of a little scale diagram, which is always useful. She went 2 meters east, 1 meter west. The net result is 1 meter east. So she's 1 meter east of her original starting position. So this vector, because of course her 1 meter east is a vector quantity, this vector resulting from this addition of two vectors is called a resultant vector. Now we could have done this algebraically as well, right? So we could have said 2 meters east plus 1 meter west, we can call east positive, so 2 meters positive, 1 meter west is negative, add them together and get 1 meter positive or 1 meter east. And that leads us to an interesting convention, right? When we go to work with vectors in an algebraic fashion, we have to decide what direction we're going to treat as positive. Really, from a mathematical point of view, you can choose any direction you want as positive, and there may be some instances where it's useful to do so. But the convention is that forward is taken as positive usually, as well as right. Up is taken as positive, north and east are taken as positive. So that's the general convention. If you want to work in any other way, you probably want to carefully define it, and it needs to be for a reason. Okay, so there's displacement in a nutshell. Very similar thing. Velocity isn't simply speed plus a direction. We're looking at this. Our average velocity is our displacement divided by our delta t, displacement over time. And so we can go back to Selma, right? And we can say, okay, she walked east 2 meters, she walked west 1 meter in 3 seconds. What was her average speed and what was her average velocity? So when we're thinking speed, again, we're thinking the history matters. When we're thinking velocity, we're thinking only about the results. So you can probably work this out pretty easily yourself. Her average speed, assuming that since she traveled 3 meters in 3 seconds, her average speed is 3 over 3 or 1 meter per second. And here's where it gets interesting. Her average velocity is very different. So her displacement is just 1 meter east. And that took her 3 seconds to get there. So 1 over 3, 0.3 meters per second east is her average velocity, even though she was never going that slow. Okay, so this gets us to a different definition. Instantaneous velocity versus average. The instantaneous velocity may never be the same as the average velocity. And we can go back through and we can look at Selma walking at constant speed and look at her instantaneous velocity. Remember, she walked for 2 seconds, she walked east. So at 1 second, her speed was 1 meter per second east. At 2 seconds, well, there's an interesting case. At 2 seconds, she was actually changing directions, so we can argue at precisely 2 seconds, her speed was 0 meters per second. And then for the last second, she was traveling west at 1 meter per second. So the instantaneous velocity can be very different from the average velocity. Okay, so that's a very quick introduction to displacement and velocity. We're going to work through the problems in the textbook tomorrow in class. I'd ask you to bring your notes template with you, and we'll collect it there, and we'll sit and work through those problems in class together. Thank you.